So one of your more common types of word problems that you'll come across with irrational expressions is something called a rate problem. And in a rate problem, what we're going to be doing is just comparing three kind of variables. So the first one is going to be some task that needs to be completed. So if you're traveling, it could be just the distance that you've traveled. If you're doing some sort of job like painting a wall or mowing a lawn, it's basically just what job it is that you're trying to finish. Or we often see this too with things being filled up. So how many containers are you filling up or draining out? Now for each one of those tasks that we're accomplishing then, we have some rate at which that's being done. So it's just the speed at which you're accomplishing the task. And then the time, of course, that it takes then to complete that task overall. Now generally we're going to be comparing multiple situations then for that task being done. And so we are going to tend to have a lot of variables for these. And so I would recommend setting up a table like this. Now this side here, you're always going to have then just these three conditions. What task are you doing? What rate is that being done? And then how much time is that taken? And then all the different situations that we're comparing, I'll put those then through as columns. And that'll just keep or help us to keep these 6 variables organized when we start to put those into two equations. So they're not required, strictly speaking, but they are a really good idea to set up a table like this. Now for each of these situations, then we can relate those 3 variables with this equation. And so the rate at which it's being done will be just whatever task you're doing over then the time it takes to do that. Now if you took physics last year, or remember all the way back to grade 10, we have our distance, velocity, time equation. The rate in that case would just be the velocity, the task would be the distance traveled, and then your time, of course, is still time. And so you have your velocity equals distance over time, and that's all this equation is. But what we're going to do is we're going to extend this. Rather than just dealing with velocities, we can look at any task being accomplished in a certain amount of time. And so we'll just extend it to there. One final note, if you're dealing with river and stream questions, if you're traveling upstream, that's working then against the current. Your net speed is going to be whatever speed the boat or the swimmer has in still water, and then minus the current from that, because the current's going to be working against you. If you're traveling downstream, now you're going with the current, your net speed is going to be your still water speed, now plus the current, because the current's going to be helping you along. So for this first one then, we have a boat that's going to be traveling both upstream and downstream. And so this is going to be just a distance, velocity, time one. And so the task that's being completed is traveling some distance. My rate then will just be some velocity, and then the time it takes, again, just still time. And we're going to look at 2 conditions. One is going upstream, and then we'll look at going downstream. And then we can just set up our table using then those criteria then. Yep. And so I just want to go back to the word problem then and kind of find then the particular values that we're going to be looking at. And just watch carefully whether they're going to be for upstream or downstream. So if we take our upstream one first, we're going to travel 20 kilometers in the upstream direction. And so it'll just be my units here. Now just watch carefully your units that they are matching up. Your speeds are in kilometers per hour and your distances are in kilometers, so those are going to match up. But just make sure that everything's in the same type of unit. Now the velocity, we know that we travel 36 kilometers in still water, but we don't know what the speed of the current is. And so that's what we're looking to find here. But I do know that if I'm going upstream, I'm going to subtract those. So 36 minus the velocity of the current is going to be the rate at which they're moving upstream. Again, in that case, the current is working against you. And we don't know the time either, so I'm just going to say time upstream. Now going downstream, we have then a slightly different set of variables. We're going 28 kilometers downstream, so we have 28 for that. Now in this case here, I still have that still water speed of 36, but when I'm going downstream, the current is going to be helping me. So I'm going to have a plus sign over there. And then of course I have the T for then the downstream going on. And so these then are going to be then the 6 variables that I have for those. And now I can look at solving them. Now we're told for this one here that it's traveling that 28 kilometers downstream in the same amount of time that it took to travel that 20 kilometers upstream. And so what that means is that this time going upstream must be equal to the time going downstream. So what I'm going to do is I'm going to relate each of those times to the distance and the velocities that I have, and then I can set up an equation that has that velocity of current then as my unknown. And so for this one here, if I'm looking for the time to go upstream, I'm going back to then the rate, which is my velocity, is just going to be distance over time. And so my time is going to be distance over the velocity, or my distance over my rate. So in this case, then I have a distance of 20, and my velocity is going to be that 36 minus the velocity of the current. Now I can do the same thing for my downstream, my velocity distance over time. And so the time is going to be equal to, again, distance over velocity. And so my time here will be then that 28, which is then the distance going downstream. And now that will be then over top of then the 36, and now plus the velocity of the current. So then I can return back to the time going upstream and time going downstream, and I can just put my variables in for each of those. And so this one here is going to be 20 over top of 36 minus that VC, and then my time downstream will be 28 over top of then the 36, and then plus the VC. And now we see we have a rational expression. We just need to solve that rational expression, and that will give us then the velocity of the current. And then we could, if we were asked, also go and find then the time by putting that velocity of current into either one of those equations, and that would give us then the time it took. But in this case, we're just looking for the speed of the current. So what I can do from this, I can take this 36 plus VC, multiply it by the 20, and the 36 minus VC, multiply it by the 28. And so really just cross multiplying there. And so I get then that 36 plus VC times 20, and then my 28 times the 36 minus VC. So we can expand that one out, and I'll get then 720, and then plus 20 VC. And on the other side, I'll get 1008, and then minus 28 VC. And I just need to collect my terms. So I can take this negative 28, and I can add it to the other side. And so then I'll get 20 VC plus 28 VC. And then I'll take this 720, and I'll move that to the other side by subtracting it from both sides. So I get 1008, and then minus 720. So this will give me then 48 VC. 1008 minus 720 will give me 288. And I can just divide both sides by 48, and that will give me then the speed of the current. And so the velocity of the current, in this case here, will be then just 6. Let's just go back to our units. Everything was in, my speeds were all in kilometers per hour, my distances were all in kilometers, and so then those units will stay the same. So this will still be in kilometers per hour. Now in this problem, we have Jason and Ben who are painting a wall, and we have the situation where Jason working alone paints the wall, where Ben working alone paints the wall, and then together painting the wall there. So we actually have 3 different situations that we're going to be looking at here. And so then we can look at, just on our columns, we have Jason working by himself, we have Ben working by himself, and then we have the 2 then together. And you can add as many columns as you need, depending on the situation. And generally, there's going to be basically 2 or 3. You can certainly do more, but our problems are going to be restricted just to 2 or 3, depending on the information given. So this case here, we don't have a distance, but we do have some work being done. And so that's going to be then what we'll have then in our first category there. And in this case, the job is just being one wall. And so it's just going to be 1 for all of those. So Jason does 1 wall, Ben does 1 wall, and together they do 1 wall. So in this case, it is just going to be one thing being done. Now, we don't know very much about the rate. We can solve for those. So we're just going to put that in as a variable, the rate that Jason spends doing it, the rate that Ben does, and then the rate together. Now, the rate that Jason plus the rate that Ben works should be the rate that they do it together. And so again, if you paint half the wall in 20 minutes, someone else paints half the wall in the same 20 minutes, then we can just add those 2 rates together to get then 1 full wall done in that particular time. Now for the time, these ones we are given the value there. So we know that Jason can do this in 20 minutes, Ben can do this in 15 minutes. Now we don't know the time it takes for them to do it together, so we'll leave that then as our variable. Now a couple of these rates then we can put together. So the rate then that Jason is doing the wall, again remember your rate is just the work being done over the time. And so Jason can do 1 wall in 20 minutes, And then we can look also at our rate that Ben is doing the wall in, and that'll be 1 wall in 15 minutes. And so we can come up with those rates then. And so what we'll do here is we'll basically try to find just what is this rate here. So the rate at which they work together, as we see here, is just going to be the rate at which Jason works plus the rate at which Ben works. Now the rate at which they do this together, again, if I do one more equation here, so the rate together is still 1 wall over whatever time they spend doing that together. So it will be the same equation, but I do also know then that that rate is equal to rate of Jason plus rate of Ben. So to get my time in there, because again, what we're looking for is how long does it take them. So we don't need the rate, we just need the time. So 1 over t. Now, the rate at which Jason works is 1 over 20. The rate at which Ben works is 1 over 15. And now again, we have a rational expression that we can solve then for this one here. So I'll put those two together using my rules for addition. So I'll get that common denominator, and then I'll get 15 plus 20. So 15 over 15 times the 1 over 20, and then the 20 over 20 times the 1 over 15. And that will give me then 300 in the denominator, which is just the 20 times 15. And so then this will be 35 over 300. I can multiply then the 300 then to this side, and then the time to the other side. And so it'll be then just 15t plus 20t. Now, of course, I could have combined that right away to 35t. So I have 300 equals 35 times my time. And so I can just divide both sides by 35. And that'll give me then the time that it takes for them to do it together. And we'll just round this to 2 decimal places. And so our time in this case is going to be 8.57. And that'll still be in minutes, because those are the units I used for everything else. And for some of them, they work out to be nice numbers. If they work out to be decimals, then you'll be told what you should round your value to. Now for this question here, we're filling a hot tub, and we have 3 different scenarios. One where we're just filling it with a hose, one where we're draining it, and then one where we're trying to fill it while the drain is open. So we have both of those working basically against each other. And so for our situations, we have just straight filling the tub, we have draining the tub, and then we have both filling and draining at the same time. So for this one here, we have a certain amount of work that's being done, which will just be filling the tub. We have a rate at which that's being done, and then we have our time here. And so then we can fill that out for those 3 scenarios overall. And again, sometimes you'll have 2, sometimes you'll have 3. So first of all, filling. We're filling just 1 tub. We don't know the rate, and so we'll just have the rate at which it's being filled. And then we have some time. It's going to take 4 hours in this one. So then if we look at draining, we're still going to drain 1 tub. In this case, that's going to take 7 hours. So then I have a rate at which it takes to drain the tub. And when they're working together, I'm still trying to just fill 1 tub, and so still 1 for the amount of work being done. I don't know the time in this case. I do, however, know that because they're working against each other, the rate is going to be the rate at which it's being filled, and now minus the rate at which it's being drained. And so watch for that sign there. They're working against each other, you'll subtract. They're working together, then you'll add. Now we do know then that the rate at which it's being filled is just going to be 1 over 4, and so that's just the 1 tub over 4 hours. The rate at which I'm draining is going to be 1 tub over 7 hours, and then working together, the rate then will just be then 1 over that unknown time. So what I can do here then is I can just set up my rates. So the rate at which it's being filled when both are working together will be the rate that it's filling minus the rate that it's draining. So the rate for both of them will be that 1 over t. The rate filling is 1 over 4, and then the rate draining is 1 over 7. And so again, I get a rational expression that I can solve. So I'll start by combining the right side of the equation, and so I'll get 7 minus 4. So it's just multiplying 7 over 7 by 1 over 4, and 4 over 4 by the 1 over 7. And then I get 4 times 7, or 28 in my denominator. So I'll get 28 on this side. 7 minus 4 is just going to be 3, and I can multiply by that time. And so then the time is just going to be that 28 divided by 3, or we could just do 9.3 if we're, say, rounding it to 1 decimal place. And so depending on what you're asked for, 28 over 3 if you're looking for an exact value, 9.3 if you're asked for a rounded value, and then your units. Because everything was working in hours, will just be hours for that.